This example, we calculate diffusion in a metal alloy, and what we have is a surface layer that we want to diffuse carbon into to change the properties to harden the material. The alloy starts out with a carbon concentration that's uniform at 10th%. And then we're going to do diffusion at 1,000 degrees. We need high temperatures to do it in a realistic amount of time. And we're going to do this by maintaining a constant surface concentration of 1.5 weight%. So we have a gas phase that deposits carbon on the surface and keeps that constant. And the question is, how long does it take before we get to a certain concentration? In this case, we're going to calculate when the carbon concentration in the alloy is 1% at a distance 1 millimeter below the surface. And we're given the diffusion coefficient at 1,000 degrees C. So essentially what we're looking at is this physical situation. Initially, if I'm plotting concentration, so I'm plotting concentration in this direction, distance into the alloy in this direction, x equals 0. We start off with a uniform concentration, 10th%. Then at time 0, we're going to make the concentration 1.5% right at the surface. And then at later times, what's going to happen, we're maintaining the concentration at 1.5%, and we're diffusing into the alloy. So at longer distance, it's still a 10th%. So this is a short time, longer time. This is the time we're interested in, where 1 millimeter in, the concentration now is 1%. So we want to calculate the time to get to this concentration profile. So in this system, we have two independent variables, the distance and the time, and then the concentration is our third variable. This system is modeled by Fick's second law, an unsteady-state equation, namely things are changing with time. So the partial derivative, the concentration respect to time, is related to the partial derivative respect to x, where d is the diffusion coefficient of carbon in their alloy. A common simplification is to assume this diffusion coefficient is a constant at a given temperature. We have to have partial derivatives because we have these two variables, and then of course we need boundary conditions to be able to solve this. And so what we write is, at the start, t equals 0, the concentration is initial concentration, which in this case is 10th%, and that's everywhere. We're assuming this is a big enough material. We're only diffusing the surface layer that far enough out, we're still going to be at the 10th of a weight%, our initial concentration. So now time greater than 0, right at the surface, we jump the concentration up 1.5%. Call that the surface concentration, and for our problem, it's 1.5%. And then at x equals infinity, in other words, far enough away, we assume we haven't changed the concentration. It's still that 1/10%. So we're assuming the slab is thick enough that we haven't diffused carbon all the way to the other end. Otherwise, these equations would not apply. So this equation has been solved, and there are books that list solutions to these type equations. And so for these boundary conditions, turns out the concentration at any point x minus the initial concentration at time equals 0 over the surface concentration minus C0 is 1 minus, it's in terms of an error function, and the square root of time and the diffusivity. And the error function is just a mathematical function that arises in a number of cases. So the error function of y is 2 over the square root of pi, integral from 0 to y, e to minus t squared dt. And so there are tables of error functions, or there are programs that can calculate error functions. So we want to use that to determine for our problem how long it takes to get the concentration of 1%, 1 millimeter into this alloy. So here I've substituted in the values. We want the concentration x, namely at 1 millimeter, equal to 1%. Initial concentration is a 10th. And the surface concentration, which is constant, is 1.5. The error function, 1 millimeter is 10 to minus 3 meters, so we want the units to be consistent. and here is the diffusivity. And so this number is, which means we could rearrange this equation. So all I've done here is the algebra. I bring the error function to the left side and this 0.6429 to the right side. Keep in mind the way I've written this, the time has units of seconds because the units in the diffusivity were seconds. Everything inside this parentheses I call y. That's equal to 0.3571. So I can go to the error function table or a program. I happen to use Polymath to calculate the value of y. Y is 0.328, which means this term here is equal to 0.0328. So the time is a large number of seconds, or 6.45 hours. So this is the time to diffuse in to 1 millimeter has a concentration of 1% carbon.